Did you notice how sometimes on a flight, when you look out of the window, the fog outside is so thick and dark that you can't see anything at all? But yet somehow the pilot still manages to land the plane smoothly without even a hint of hesitation or fear. So exactly how does all of that happen, and how do they do it? For which the secret lies in an advanced technology that not only shows the pilot the right direction, and also guides them straight to the runway with pinpoint accuracy, even in zero visibility of 0 meters. This autoland technology in modern jetliners is so advanced that it gives the pilot a complete virtual view of the runway from air, so they can land perfectly without even actually seeing it when the runway and airport is covered in dense, thick fog and thunderstorm. In this video, we'll know what this technology is, how this technology works, the sensors and instruments that make autolanding possible without any human intervention, and why it's considered a game changer for aviation safety and low visibility operations, and what upgrades could make it even more powerful in the future. Let's dive in. Before going deep into the topic, let's first understand what zero visibility actually means, because this term is often used in aviation. Zero visibility is when a pilot cannot see the runway or its surroundings at all from the cockpit. This can happen for many reasons, such as dense fog, heavy rain, snowfall, or sometimes even due to dust storms. And in some rare cases, volcanic ash or industrial smog can make visibility even worse, turning a smooth landing into a serious challenge. Yet despite these dangerous conditions, modern airplanes can still land safely like a butter, which is made possible by something called the ILS, that is Instrument Landing System. The ILS is a radio navigation system installed on the ground that guides the pilot using radio signals. It tells them where to go, what altitude to maintain, and how to align perfectly with the center of the runway. Now imagine, without this system, pilots would have to rely only on their experience and a few basic instruments, which could be extremely risky during low visibility operations. The ILS mainly transmits 2 types of signals. First is horizontal guidance, known as the localizer, and second is vertical guidance, known as the glide slope. The localizer is a radio signal transmitter placed at the far end of the runway, which sends out 2 narrow beams, one to the right side of the runway and the other to the left. The exact point where these 2 beams meet is the runway's precise centerline. Inside the cockpit, the pilot's instrument panel has a special display with a needle indicator. This needle shows how far the plane is from the centerline. If the plane drifts too far to the left, the needle will move to the right, telling the pilot to steer right. And if the plane is too far to the right, the needle will shift left, signaling the pilot to adjust left. This system is so incredibly reliable and precise, with an accuracy of less than 1 degree, which means the pilot gets near-perfect guidance to keep the aircraft exactly in the middle of the runway, no matter how thick the fog is or how dark the night. No matter if he can see everything outside his window or if he sees nothing outside his window. But the risk here is that a plane approaches the runway at a speed of 130 miles per hour. That's fast and dangerous at low altitude, and just moments before the landing, pilot has to be in an established approach to execute a successful landing. That is why the preparations to land begins way before the actual landing in the cockpit, and pilots need sufficient time and distance from the runway to calibrate their aircraft autoland. Which means the radio signals of this high-tech instrument landing system has to go far from the airport so that the aircraft, which is configuring itself to autoland, can catch those signals and get into an established approach position to land safely. Due to which the localizers are installed with such powerful emitting rays that can reach between 20 and 30 miles, allowing the pilot to start aligning with the runway from a long distance away. Now, the second major component of a successful autolanding is the glide slope, which is another radio signal transmitter, just like the localizer, installed at the side of the runway, just near the critical touchdown point. This system also sends out 2 radio beams, one angled slightly upward and the other slightly downward. The point where these 2 beams intersect forms the perfect descent path, usually set at a 3-degree angle relative to the ground. This is considered the ideal slope for a safe landing. Inside the cockpit, there's another display showing the pilot exactly where the aircraft is in relation to its ideal glide path. If the plane is too high, the needle will drop down, signaling the pilot to increase the descent rate. And if the plane is too low, the needle will move upward, telling the pilot to raise the nose slightly to align itself on the ideal glide path. When the localizer and glide slope work together, they create an invisible 3D corridor guiding the aircraft smoothly and safely to the runway. These systems are so advanced that even in complete zero visibility, the landing can still be executed with precision. And in case if things go wrong, modern aircrafts also have backup tools like DME, which is called distance measuring equipment, that tells the pilot the exact distance from the runway at any moment. Now, the ILS isn't just a one-size-fits-all system. It's divided into different categories so that pilots can get the right level of guidance depending on visibility and landing conditions. These categories are defined by the International Civil Aviation Organization, the global body that sets aviation safety and operational standards. According to ICAO, ILS is divided into three main categories. These are Category 1 ILS, Category 2 ILS, and Category 3 ILS. Category 1, also called as Cat 1 ILS, is the most basic of all and is used in moderate visibility where the decision height for the pilot is 200 feet, meaning that they must see the runway well in sight from 200 feet of altitude and make the final decision on whether to land or abort the landing and perform a go-around. In Cat 1 ILS, the runway visual range is between 1,800 to 2,600 feet, meaning the runway must be visible up to this distance. This is suitable for clear weather or light fog, but it doesn't work well in dense fog or heavy rain weather conditions. And that is where Category 2 ILS, also called Cat 2 ILS, comes into the picture, designed for ultra-challenging weather conditions. In this, the decision height for the pilot is between 100 to 200 feet, and the runway visibility is between 1,000 to 1,200 feet. The pilot may have to come even more lower than Cat 1 to see the runway in foggy and rainy conditions, which is dangerous when you can't see jack shit out of your window. But the system gives the pilots adequate guidance so they can descend to such low altitudes safely even in low visibility. Now, there are times when things get even worse than this, where the visibility gets down to literal zero. And that's exactly where Category ILS comes to the rescue, as it is the most advanced auto-landing guide and is designed to let the autopilot of the aircraft land the plane weighing 100 tons completely by itself without any human intervention and complete zero visibility. Now, Cat 3, being this capable, is further divided into three subcategories called as Cat 3A, Cat 3B, and Cat 3C. Cat 3A has a decision height of less than 100 feet and an RVR of 200 meters or more. Cat 3B has a decision height of 50 feet or less and an RVR as low as 50 meters. Cat 3C has no decision height and no RVR limit, meaning landing is possible even in zero visibility. However, Cat 3C is not used in normal passenger, private, and commercial flights because taxiing after landing also requires some visibility, due to which it is banned to use Cat 3C Autoland under normal low visibility operations. In a way, each category makes landings one step safer. Cat 1 for basic conditions, Cat 2 for bad weather, and Cat 3 for the most extreme conditions. Now, after understanding that with the help of an instrumental landing system installed at the runway and in the plane together helps the pilot safely land in zero visibility, let's now understand that how ILS actually works. See, when a pilot approaches any runway for landing in zero visibility, they follow the ILS signals, which are emitted from the end of the runway towards the ILS systems installed in the plane. The ILS displays in the cockpit keep updating constantly in real time, guiding the pilot about the exact runway position and the correct descent path. If the plane drifts even slightly from the path, a warning appears in the cockpit, allowing the pilot to take immediate corrective action. In advanced conditions like Category 3, the landing can even be fully automated, as we have discussed. Apart from ILS, there are other technologies like ground-based and satellite-based augmentation systems that enhance navigation accuracy. Still, ILS remains the most reliable and globally accepted system. In the future, AI and machine learning could make ILS even smarter through predictive weather analysis. So now you know just how important ILS is in modern aviation. If you enjoyed this video, don't forget to like and subscribe to the channel. Thanks for watching, folks. I shall see you again in the next one.